Welcome in, everyone. Thank you so much for joining this session. Please help me um, give a virtual warm welcome to Indra. And also keep in mind that you can chat. So feel free to ask questions and drop your thoughts in the chat. Welcome. Take it over, Indra.
Thanks, Patricia. Appreciate it. Hi, everyone. Welcome to my session. I'm Indra. I'm Indra. I'm going to talk about time series analysis for coupled neurons today. So, just to say that, like, I'm not going to assume that everyone knows what these terms mean. So, as we go along the slides, I'm going to describe this, point by point. Also, there are going to be some slides and there is going to be a notebook as well. So if you have um, some time to go into the link and access the notebook, that would be awesome. I'll keep this up for a few seconds. I can also drop the link in the chat if that's all right. Moving on, I'm Indra, and I'm currently based in University College Dublin in Ireland. So if you want to know a bit more about me, you can go to my website, which is that link, my GitHub page. And if you have any questions after the tutorial, after the session, and you want to send me some email, that's my email ID. I'm happy to take questions through emails as well. Okay. This is my first PyData conference, so I'm very excited to be here, and I want to thank the organizers for organizing this global event, which is not a very easy task. So hats off to them. Um, uh, so a bit of motivation about this tutorial, and excuse my use of cartoons. I'm a bit of cartoon nerd, so as you can tell. So yeah. I'm going to talk about neurons mostly, and neurons, they produce rich nonlinear time series data. So time series data is a very rich data set that a lot of data scientists nowadays use for their analysis purposes. And you can find most of the times this complicated time series data that you'll come across, they have some hidden coupling between the variables that you study. And they appear everywhere. For example, in physics, in biology, in finance, and in engineering as well. We have a very famous tool, that's Python, that makes our life easy, like analyzing this data because of the open source community and like whatever the community has been doing for the last few decades, developing different open source tools and whatnot. So I personally have found Python to be very useful, and I'm gonna give you a flavor of what I do from time to time using like analyzing neuron data and building mathematical models. Uh, Time series analysis also help bridge models and messy data because as you can tell that building mathematical models from messy data can be messy, and it might not always give proper models that you want to work with. So time series analysis bridges this gap quite properly. A bit about me: I did my bachelor's and master's in physics, and I got my PhD in applied math in New Zealand. That was in 2024. I also did my first postdoctoral fellowship in New Zealand until August 2025, which was this year, when I moved to Ireland to University College Dublin as a research fellow, but in mathematical neuroscience. So you can see like there has been a bit of digression from time to time as my academic career evolved. However, there has been one particular topic that I have always worked in, and that's called dynamical systems. So, what are dynamical systems? So, dynamical systems are any systems, like any system that evolves in time. So, any system that evolves in time will give you a time series data, right? And so, what these usually are is like a rate of change of a particular physical quantity that you are interested in, that you want to study, that changes in time. Now, many physicists, or I would say applied mathematicians and engineers, they try to like study these systems by building models given an initial timestamp. So you have to have like the initial behavior at a particular time t naught, and then what they do is like they try to come up with a function f which depends on this particular quantity that you are interested in, and also time. This is just a mathematical notation of writing like ordinary differential equations, which is called x dot, which necessarily means the change in the quantity x with uh, the change in time. So d is actually the change, the rate of change. So it was Newton and Leibniz who formalized this concept of dynamical systems and like created these mathematical tools. Um, they actually wanted to study planetary motions. So that was the whole motivation behind developing these tools. However, now you can find dynamical systems and time series in almost any field that you come across. So it's quite evolving. Okay, I want to give another disclaimer that my talk has nothing to do with AI kind of thing. Like I'm not using any AI sort of like agents or those kind of things. So I'm not gonna talk any. So if you're here to learn about AI related stuff, my talk is not that. So just to give you like a heads up. Okay, time series. As I was saying, like it can be found everywhere, like everywhere around us. And for example, in stock prices, in sports, for example, I have worked with like this tracking data from football, like soccer games that you that gets tracked with respect to time. So there are this like player movements that get tracked with respect to time, and it creates a rich data set that you can analyze and come up with different models to uh, like advise managers or like teams. You can find time series in medicines as well, in weather measurements, like rainfall data, which is also a very rich data set that people work in from time to time, and especially neuroscience. And this is my focus. So that's my interest, like my recent interest. Okay. Neurons. So I'm pretty sure everyone knows what neurons are, but I'm just gonna give like dive a bit into the biological aspects of what neurons are, so that you get a bit of flavor of what I'm talking about. Neurons are the fundamental units of the nervous system that helps, like that drives our like everyday mechanism, I would say. And what happens is billions of neurons, they couple through this functional structure called synapse that you can see here. I've taken this picture from this website, which does a very good job in like giving a pedagogical overview of what neurons are and what synapses are. So what synapse does, it connects two neurons, and then it propagates the signal from one neuron to the next neuron. So that's what its job is. um, so the neuron on the left, it's called a presynaptic cell, which is before the synapse, that's why the name. And then the neuron on the right is called the postsynaptic cell, so the neuron which has received the signal from the previous neuron through the synapse. And this synapse, the functional form of this synapse can be quite complicated, and that gives rise to coupled time series from neurons. And their mechanism evolves in time, and thus they can be perceived as dynamical system. So you can build models, like mathematical models, and study them, study the time series from these models. Now, one particular aspect of dynamical systems that I'm quite interested in, and I got my PhD in, is chaos. So, in popular term, chaos means a state of disorder, um, as the name suggests, right? Like it's pretty evident. But in mathematical term, what it actually means is like the system is very sensitive to initial conditions. So what happens is with change in the initial condition, like with a very little, like with infinitesimal perturbation, the final result will change quite a lot. That's why it's very sensitive to the initial condition. And when you try to like plot these dynamical variables against one another, you'll see that on the plotting window, the when you plot it, it fills up the like the plotting window densely. So it's like a dense orbit that you can see here. So this is a very famous example from, I don't know whether you can see the double rod, but it's a very famous example from physics that people get taught in undergrads physics. So it's a double rod pendulum, and so one pendulum is connected to another as well, and then when you try to like give it a sway, after some time it starts giving like doing some chaotic motion. So that's what it is. So that's what a chaotic dynamics is. Chaotic systems, they behave predictably in the beginning, but as time goes they start becoming random. And this kind of behavior also has been seen in neuron models and neuron dynamics. Okay, this is a Python conference. So I have to showcase the packages, the Python packages, the open source packages that I use heavily and rely my life on, I would say, from day to day, because that's what my research is all about. I'm a heavy Python user, I would say. I develop codes and like make everything open source as well, but I'm not a software developer. So there's a boundary between what I do and what software engineers are. Okay, so I use NumPy for numerical nitty-gritties in Python, and then there is SciPy, the scientific Python suite. Uh, this is the most important package for data scientists, I would say. One of the most, okay, let's not say the most, but one of the most important packages, which is pandas, um, for cleaning the data, doing some data handling and all sort of magic. And then our very favorite, very own matplotlib, without which you can't visualize any results. So that as well. So these are the main four packages. uh, Before I start the like going deeper into the technical aspects, I want to say, like, don't get thrown off by the mathematical equations here. It's just an example, but what I want to emphasize on the fact is the time series. Yep. So I'll just give an overview of what these are. So there are different mathematical models that have been developed over time. So there's a recent model that I have quite studied, which was recently popularized in 2018. Okay, in scientific term, it's not quite recent. I would say 7 years is a long time, because the way science is progressing nowadays, I would say it's quite old. But yeah, this is one of the models that I quite like. So the X term here, it models how the action potential or the voltage of a particular neuron, they evolve in time. So when a neuron fires, it has to like has have a voltage, right? So after it fires, then it needs to recover. So that's what the dynamical variable y represents. So it models how the neuron recovers after it has fired for a time. And then it's it is driven by, so the voltage is driven by a current term, which is given by this model, which is somehow dependent on the voltage x. Yeah, so that's it. Like these are the dynamical variables, and we'll mostly be focused on the voltage aspect of the neurons, and which is x. So we'll look into the behavior of x mostly. Now you can plot x. Sorry, I keep on doing that. You can plot x against y, and that gives you a phase portrait. So that's what it looks like. And when you plot x against time, that's the time series. So that's what this tells you. So these are the neuron firing, and then it slows down a bit, and then again it keeps on firing, like bursting, and then it slows down a bit. So this is a simple mathematical model, and parameters selected. So okay, here are four different parameters that you will see. So the one is A. These are the model parameters: alpha, gamma, and epsilon. Now you can do parameter fitting to come up with these parameters using real world data, and real world data can get a bit messy. But people have already done that, and I'm gonna select some particular values of A, gamma, alpha, and epsilon to show you that like how it behaves. But these parameters should be empirically informed. So that's what I want to emphasize. uh, this this model does capture the realistic bursting phenomenon in neurons, and then it also portrays a battery of complex dynamics that you'll see soon. I want to show that to you, though that's the main topic of this talk. uh, I also want to tell you that like there is just a single liner from the SciPy package that helps you solve this kind of mathematical equations, which is solve IVP. And IVP stands for initial value problem. So initial value in the sense like the first timestamp that you need to provide to the function. And once you define this in Python and put it in solve IVP, it will solve it for you. It comes from the scipy.integrate suite. It's quite handy, and I use it from like almost daily. Okay. Yeah. So George Box did tell us that like all models are wrong, but some are useful. So while coming up with mathematical models, we should always keep this in mind. I try to remind myself this from time to time, and I'll also show you some examples if time permits. That you know there are some models which work very well according to the realistic behavior of neurons, but there are some models which do capture the behavior of neurons but in a very local region. So it can't capture like in a very broader general region. So all models at some point start failing in a way. And that yeah, that's the takeaway from this slide. And we should every one of us who does data driven modeling should keep this in mind. Okay. Now a bit of Python code snippets. We will do this in Jupyter Notebook as well. Just want to show you like how you can just transform uh, the 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 model that I showed into Python. So you need to define the parameters. So I've chosen some particular parameters here, which is A, alpha, gamma, and epsilon. Then you define the function of the differential equations, the right hand side of the differential equations that you saw here. So 1, 2, 3. So you just define a function and like write it down, and then you try to collect the data from at time t. Now, as I said, like you need to provide some initial conditions. I'm randomizing the initial value for the first voltage timestamp. uh, this is helpful in the sense that like it gives you more robustness when you try to test your program, and like when you try to test your model. When you randomize the initial condition and then run different simulations, then you can see whether the final behavior acts in similar qualitative way. The initial conditions you collect in this list, and then you also need to define a time span for the solution. So I have chosen 0 to 4000. And how many timestamps do you want? So this is also a bit of testing procedure, in the sense like you can provide more timestamps, in the sense like that will reduce mm, uh, the time step size. That gives you a bit more like smooth dynamics, but after some time it stops mattering too much. So you have to have a trade-off of what value you choose. But for here we'll just keep it like this. and then you solve. So this is the particular solver Python program. It's just a one liner, and you can see here you're just feeding the system that we defined in solve IVP. You define the, like, you feed the time span, you feed the initial conditions, and the time evaluation, and then you choose a particular method. Here I'm showing RK45, which is a very, like, commonly used integration, like numerical integration method for solving differential equations after Runge-Kutta. There are other methods as well, and I would try to point out, like to point out here that RK45 is not the best solver, I would say, because some solutions, like some differential equations like this, can become stiff at some point. But for now it's all right. We can run the simulations with this RK45, and then we can test with other methods as well. After you do that, you extract the solutions which you have here, and then you collect the timestamps as well. That's what you do with Python. So that's just for one neuron. Yep. Now we are interested in coupled neurons. So that's what my talk proposal, like the tutorial proposal was, time series analysis of coupled neurons, right? And you already saw this picture before, and I showed you that there are two neurons and they're coupled by a synapse. And now if you magnify into this synapse, there are two commonly biological phenomena that goes on at this synapse. So the first one is called electrical synapse. So it's just a very simple exchange phenomena between one neuron and the other. So this is the end of the presynaptic neuron, so that magnified version of this, and that's the start, like the tip of the postsynaptic neuron, which has been magnified here. And you can see like the transmission of excitation, so how the signal is getting propagated from one neuron to another in both ways. So it's a bidirectional mechanism, is shown by the arrows here. And so this is called a gap junction coupling, or like an electrical coupling. uh, so that's what it is called. But the synapse could be a bit complicated as well. Sometimes what happens is, instead of just being electrical like electrical signal propagation, signal can be propagated through this like this biological objects called neurotransmitters. So these are chemicals, I would say. And what happens is, like, you see at the end there are this pockets or packets of neurotransmitters that get propagated to the end, and then they burst there, and then the neurotransmitters get released, which are then picked up by the the tip of the next, uh, like the post synaptic cell. One subtle difference between these two is this, the direction is so it's unidirectional. So what happens is, like, the signal gets propagated just one way. Yep. So it gets like it propagates from the first neuron to the second. Okay, any question till this far? I just realized that I have been talking quite a lot, so any question? Just want to ask the host, Patricia, do you think everything is all right? You can hear me properly? And
Yes, I can hear you. Can you hear me?
yes, I can hear you as well.
Okay,
Yep.
yeah. Let's see. Yeah, you have quite a bit of while. Um,
Okay.
yeah, your session will end.
In 57 minutes, I would say. Right?
Yeah.
Yeah. Okay. Yep. Yeah, I haven't yet touched on the Jupyter notebook, but yeah. Okay. Couple neurons. That's what I was talking about. These are That's how two neurons are coupled to each other, and it's just two neurons. And what happens is, the brain is very complex, and it's billions of neurons that are connected through different synaptic connections, very complicated connections that you can see here. This is just between two neurons. Now you can build toy models, and building an electrical coupling is very straightforward, I would say. So what you can do here is like you have, so I is now the neuron number. So for this case, we have two neurons. So I will run from 1 to 2. And this is the left neuron, or the presynaptic neuron, and that's the right presynaptic neuron. Sorry, the postsynaptic neuron. And theta is the coupling strength. So there's this strength between two neurons by which they get coupled. So if it's a very strong, whether it's a strong coupling or a weak coupling, and also depending on the sign of theta, whether it's positive or negative, you can differentiate whether the coupling is excitatory or inhibitory. So if the coupling between two neurons is excitatory, that means uh, they excite each other. But if it's an inhibitory coupling, that means one neuron is inhibiting the voltage propagation of the other neuron. That's the basic notion. It's quite more complicated than that, but like for modeling purpose, we can think of in that way to start with. Now here, that's the coupling term. So you can see that it's just a difference between uh, the voltages of the two neurons, right? So what that means is, it's just modeling the bidirectional electrical coupling. So that's how it happens. Like ions get exchanged between two neurons, and it's very simple mechanism. And you can model this using just the difference between the voltages of the two neurons, because there is always a gradient, and the gradient gets captured from the difference. Now, for the chemical coupling, however, the coupling strategy is more complicated. And after a lot of modeling strategies that people have developed throughout the years, this is the modeling strategy that quite matches chemical coupling. So it's a sinusoidal, sorry, it's a sigmoidal function uh, that models the behavior of one neuron chemically coupled to the next. Now, when I ran a time series analysis on the chemical coupling, this it might give some unprecedented results as well, because, as I said, not all models are correct. So there are some people have also developed different, try to make these coupling strategies more realistic over time, and they have included periodic behavior, like they have tried to inculcate periodicity on the current, and then like see how this periodic, like this non-linearity, um, like you know uh, like affect the behavior of two neurons coupled to each other. So you can do all sort of things. You can make them more and more complicated, but again, like it you not like you don't necessarily need to complicate your models to make it more realistic. So that's also one takeaway that every modeler or like data analyst should keep in mind. Yep. There has been other approaches to bring into effect electromagnetic effects, in modeling electromagnetic effects between two neuron couples, because um, in our brain there's always electromagnetic like signals, uh, like affecting the coupling between two neurons. And mathematically modeling them is also not quite easy, but there has been approaches, and they do quite work well when you compare them with data. There are some other nitty gritty that you can also look into, but I'm not going to talk too much about it. That's higher order coupling. So instead of like two neurons just coupled to each other by a single line, like a pairwise coupling, there can be a more complicated surface coupling. In the sense, you can see not only that the red neuron is connected to green neuron, but these three neurons, they come together, like the red, the green, and the black, to create a surface coupling, which is whose strength is given by theta. So modeling this makes the system more realistic but more complicated. So as you can see, the equations become more and more dense, and you don't want to do that. So like it depends like what you want to do, but uh, you don't want to increase the number of neurons beyond 4, or like let's say 5, and that will make your life hard. Now, as I was talking before, I was talking about how you can just translate uh, the systems, like the mathematical systems, into Python code. Now these are code snippets for doing similar thing for the couple neurons. So I'm just talking about two neurons coupled to each other, and this is the same equations that you see here. Instead of three equations, it would be six equations. And then that's what you do here. You collect the data from running the system, and this is for the chemical coupling, and that's for the Josephson junction coupling, the more nonlinear coupling strength. So now, time series. So that's the main topic of the of today's talk. So when you run these simulations, you will see there is a time, like a time column, which is the timestamp, and then the voltage of the first neuron, that's x1. So it's a time series, and then the recovery variable of the first neuron, and similarly the voltage and the recovery variable of the second neuron. And then you can plot these different things, the phase portraits, the time series, and a coordinate transformation, which tells you whether the neurons are behaving in a regular fashion or like in chaotic, uh, complicated, complex behavior. There's some So next we'll see how we can quantify this behavior from the time series data that will get generated from the simulation. So there are 5 tools that I'm going to talk about, and I have recently written a tutorial paper on this, and I'll share the link at the end, which will be a part of the slides. So the first one is Hurst exponent, which measures persistence in time series data. The second one is an entropy measure, which tells you how complex the time series data is. And then there is this test called the 0-1 test, which measures whether there is any chaotic behavior in the neuron, and what can we do about it. And then you can, when there are multiple neurons, this concept of synchrony comes up quite often. So because that's a very important medical scenario to know about, and people have studied quite a lot how two neurons or like multiple neurons are synchronized with each other. So there's a very simple way to do that, depending on your problem. We will look into this cross correlation function, which is a variant of the Pearson's cross correlation coefficient. And then there is another parameter which is called the Kuramoto order parameter after the scientist Kuramoto, the Japanese scientist Kuramoto. And what it does is also it measures the synchrony between two neurons, however not in Euclidean space but in like a phase space. But yeah, that is pretty much does the same thing. So just an overview of what these tools are. Hurst exponent was first introduced by Hurst in terms of hydrology, but since then it has been used in climate, in financial problems, and then neuroscience as well. What it does is like it measures the time series memory, the long-term memory of the time series, and also like, which means persistence in the time series. I'll just tell you what these are. So it can be computed. So there's a huge algorithm of how it can be calculated. Just emphasizing the last step here. So what it does is like it computes using this analysis called the rescaled range analysis. There's a very good paper on that, and it's the expected value of two functions of the time series with respect to time. And they calculate the expected value of the ratio, which is proportional to the exponential increase of this function. And that's the exponent h, and it lies between 0 and 1. And if it lies between 0 and 0.5, that means the time series is anti-persistent. That means uh, at particular time t, if the time series is showing like a lowering trend, then at the next timestamp it can show like an increasing trend. So the trend at time t plus 1 is not dependent on the trend at time t. So that's what anti-persistent means. It's somehow related to chaos and more complexity. If h is more like close to zero point 0.5, then it's a random walk, more chaotic behavior. And but if it's between zero point 0.5 and 1, that means there's a positive dependence and more regular time series. So at the if the trend at time t is increasing, that at time t plus 1 the trend will also be increasing, and vice versa. Sample entropy was proposed by Richman and Morvan in 2000, and this was proposed for a medical reason as well, and it was for cardiovascular data, if I'm not wrong. Yes. What it also does is like it assesses the complexity of time series data, especially biological data, and it does some. Again, it has a bit of lengthy algorithm, but it calculates the negative logarithm, like negative logarithm of these two functions, and then limits it at like a large data set. A higher sample entropy indicates higher complexity, which is related to chaos. And however, the way we have we have used sample entropy, we have not normalized between 0 and 1. I just want to give you a heads up, but it can be normalized between 0 and 1 to give it more proper meaning. Now, there's a package that this gentleman has written in 2019, which is called Nodes, and you have to download this package to run the simulations. And it stands for nonlinear measures for dynamical systems, which is heavily based on NumPy, and it provides different functions for directly implementing the Hurst exponent and also the sample entropy. And there are other functions that you, if you're interested, you can look into. This one-liners called Hurst RS and Sampen from Knowles. There are other sophisticated tools as well. If you're interested in it, have a look. Then there's this test called the 0-1 test for the time series data. And the first thing you can do regarding this is like you can translate the voltage variable into some other coordinates, which is called P and Q, and then just plot P against Q. And then you can eyeball the plot and it just say whether this is chaotic or not. But that also gives you more control over deciding whether your analysis is giving the right quantity. You can compute a mean square displacement term from this, and then a correction term. And over that, you compute the growth rate of the time series, and that lets you quantify chaos. Again, I'm not detailing all the mathematical nitty-gritty, but if you're interested in it, you can read their paper from 2019 to 2016. But if k is close to 0, that indicates regular dynamics. That means the behavior of the time series would be bounded. If it's k in uh, tending to 1, then it indicates chaos. There was a Julia package that was written for this purpose. One of our students translated this to Python 3 years back or 2 years back, when we were not that heavily reliant on ChatGPT. So we have since been using the translated version, which has been written in Python. I don't think it was necessary, but just to keep everything in Python, we did that. So what was done was like we used curve fitting and the solver function fsolve from the optimization suite from SciPy. We also used Pearson R function to compute the Pearson's correlation coefficient from the stats suite of SciPy. Then for the cross correlation coefficient, which has been proposed by many authors in different forms and formats, you take two time series and just calculate the correlation from this formula. So here, this is the mean over time, and that's the mean over number of neurons. It's just 1, 2, 3, 4, 5, 6, 7 liners to compute the cross correlation coefficient between two voltage time series. Again, how to quantify that? If the absolute value of gamma, which is the cross correlation coefficient, is 1, it indicates total synchrony. If it's less than 1, then it's asynchrony. Moreover, gamma equals to 1 represents the fact that two neurons are synchronized in tandem and they are in phase. And if it's -1, that means they're, even though they're synchronized, but they're out of phase. And you can see those kind of behaviors quite often as well. Similar thing for Kuramoto order parameter. So you translate the variable into a phase variable and then do these two things. And like, I just want to emphasize on the fact that it's also like not more than 5 liners. You can actually do this in 1 line, but did break them down so that it makes it's easy to make sense. Again, when B is 1, this means the nodes are all fully coherent and the phases are all locked. Any values less than P represents that they are not synchronized with each other. Okay, it's time to move to the notebook. Oh, I have 40 minutes. So if you click on the link, it will take you to that. Just want to tell you the fact that I had a binder link as well, but it was being a bit clunky yesterday. So some of the packages were not running. I don't know why. So I removed the binder link, but I have an Google Colab link as well. So if you want to run it on your local machine, go for it. I think running on your local machine is easier, I would say. But in that case, you need to download the extra package nodes. I'll show that to you. But you can also run it in Colab. So I'm gonna. Okay, sorry. Just gonna go back. Link in new tab. And also note that running the notebook from Google Colab might be comparatively slower than running it on your local machine. So yeah. But it doesn't make that much of a difference. There's a Shiny app that I have written recently. This is still a work in progress for this, because not many people want to look into the code. They just want to click buttons and see the behavior. However, there is a caveat. I don't have money to buy the paid version of SciPy. Sorry, a paid version of Shiny. So if there is more than 2 people who are trying to run the app at the same time, it might not work. So I'm sorry for that. But this is again a work in progress. Okay, moving on to the Jupyter notebook. Um, Yes. So, okay, there was a question which has been asked. It says like, does the use of coupled neurons for solving problems have a connection with artificial neural networks? So AI, that's both shallow and deep. You can draw some correspondence, but of course, like artificial neural networks were like built being like motivated from real neural networks, right? So yeah, there is a particular correspondence, and the weights that you see in the artificial neural networks, they somehow relate to the coupling strength. So that's a direct correspondence that you can draw. Yep. Okay, moving on to the notebook. You install the, okay, run anyway, install the package. Oh, it successfully ran already, sorry. Downloading. I might not have time to go through the whole notebook, but this is online. You can run every cell as well, but I'm gonna show you a few examples. So yeah. Okay. Then you need to import the packages. And then I have put the equation for the single neuron here. It's just this is just a Python version of converting the equations with the initial time point and everything that I showed in one of my slides. So you run it, you collect the solution and the time series as the timestamp, and then using Python Matplotlib, you just plot them. So that's what it is. You can also change the certain parameters if you want, or the initial conditions if you want. For example, you can make it 0 0.3 uh, gamma. It's done. It gives a different behavior. Let's make 0 0.315. You can change the epsilon as well. It's done, and it gives very different behavior than what you saw. You can make it even you can make it smaller, by the way, instead of making it bigger. uh, and again, like, it gives very different chaotic attractors. Okay, this is not chaotic, but it gives different attractors and like different looking neuron spikes, neuron voltage spikes. Let it bring back to what it was before. And here you can see like the recovery is happening in a proper time scale, in a significant time scale, I would say. Now, these are different helper functions that you need to run the code for the chaotic behavior, the 0 1 test. So you need to run that cell. Then we'll go on to gap junction coupling. Here I have uh, written the function in a way that you would just need to include the so the input is the theta, which is the coupling strength, as you can see here, and you collect the behavior and you study the behavior with changing theta, if you may. So you have to run this. As you can see here, it's the similar thing. You have the system, you have the initial conditions for all the, like, both the two neurons, and each neuron has like three dynamical variable that they need. And then you collect the initial conditions, you provide the time spans and everything, and then you run, you solve the solution, solve the differential equation, and then extract the solutions and the time stamps. And then you do all sorts of like metrics. The code snippets that I showed you before for cross correlation coefficient, Kuramoto order parameter, the 0 1 test, and then the one liners for sample entropy and Hurst exponent. So to run these codes in Google Colab, it takes 1.5 minutes. So if you run this cell for a particular theta, if you go here and so I'm choosing -10, which is a inhibitory coupling strength, like a very uh, so the two neurons are highly inhibitory to each other. So if you run this, it's gonna execute soon. So it's running. Gives me a break to drink some water. So the computing of the cross correlation coefficient gamma and the Kuramoto order parameter beta is done. B, sorry. The next thing that it's gonna compute is the the chaos quantification. Yeah, so I'm just gonna emphasize on the fact that like these things are it takes a lot of time to compute, like run the simulations and everything, because of the complicated dynamics that it has, and also the mathematical model that you have come up with. So then extra complexities come on the number of neurons. Okay, now it has done computing the 0 1 test. So extra complexities come when you include more and more neurons. We'll show how to like, handle that, and also different coupling strategies, and also how many timestamps that you have. So it depends on a lot of factors. Now the Hurst exponent and sample entropy is also calculated. You see the time series that it generates, and then it generates all the quantifications and gives you visual representation. So as you can see here, the time series is very chaotic, right? So it's like firing randomly over time. And so this is the phase portrait. Even looking at the phase portrait, like plotting the voltage against the recovery variable for the first and the second neuron, you can see that like they're not quite bounded. For example, here as well, this is the translated variable. You can see that the behavior is a bit all over the space, but it's not that chaotic. However, it is quite chaotic. So you see the chaos value is close to 1. So our quantification is giving proper value. The sample entropy, okay, so here the sample entropy looks small, which is 0.15, but it is not. So because as I said, it's not normalized, it would be good to normalize it. But I have run some more numerical tests, and the smallest it can get is like in the order of 10 to the power minus 2 or minus 3, which is quite small, but this is not small for sample entropy. So it's a big value of sample entropy, which indicates high complexity, for which is intuitive, right? Like for a bit chaotic data set, you will get high complexity. And the Hurst exponent is less than 0.5, which means the time series is anti-persistent, which also is intuitive, right? That means the timestamp at uh, time, let's say 1000, is not following the trend of the time series at time 999. So because the reason being it's chaotic, so all these quantities are giving you the right sort of characterizations. And having more than one quantity to characterize the time series is quite important, because that gives you a more robust decision. So like you can, so your decision making would be very, like, would be how to say it, like properly informed, and you would be more confident. And then again, so this gamma tells you how synchronous these two neurons are, and they are not. That's why you're getting like minus 0.2. If they were synchronous, you would get something close to 1. Now the b value is 0.94. Again, it's not close to 1, but this b value can, if they were, like, very very synchronous, then it would get close to 0.99, something like that. But again, these quantifications might also not be quite, like, capturing the behavior of the time series, because these are very time series dependent. Let's try with another coupling strength here. Instead of minus 10, we can try a very weak coupling strength, let's say 1, which is close to 0, and let's see how it behaves. We run it again. Need to just wait for 2 minutes. Yeah, it doesn't take quite 2 minutes, but slightly less than 2 minutes, so it's not that bad. I would love to, like, optimize the timing of this, and that's one of the future works that I'm gonna mention about. Uh, but it gets quite complicated, and you can't actually parallelize the whole simulation because of this coupling between two nodes. So if you ask the two different nodes from your computer to run separately parallelly, it can't actually do that because they're somehow connected to each other, right? Because of the coupling strength. So yeah, like using parallel computing is not an option. Yeah, so that's something to look into as well. Okay, cool. Now you see the behavior is becoming more regular. So these two neurons are, like, acting in tandem. They're showing some bounded behavior, and also the translated variables show some boundedness close to mm, the center, 0 comma 0, and the origin I meant. And you can see this is bounded close to the origin for both the neurons. Now the sample entropy value has reduced. It's like 0.075. The complexity, that means the complexity has reduced. The Hurst exponent has become more than zero point 0.5 as expected. So that means the neurons are becoming more and more regular. And you see the k value has reduced quite a lot from close to 1, which meant chaos. But here it's showing a value close to 0. That means it's regular and it's capturing very well. Now for these two neurons, you can see, like, just eyeballing them, you can see that they are behaving quite similarly, even the x values, and they seem to be synchronous with each other. Another way to just do it is like plot x1 on top of x2 to see like whether they totally match. The cross correlation coefficient value is 1. That means they're highly correlated and highly synchronized with each other. And also the order parameter gives a value very close to 1, which is 0.9985, instead of 0.94 or 5 that you saw for the last simulation. They're recovering at the same time and also firing at the same time. We'll try another zeta value, which is so now the two neurons are exciting each other, so they're highly strongly coupled and also exciting each other. And I think they intuitively they should be more synchronized and more regular. So this actually makes more sense, because when two neurons are like inhibitory, so one neuron is inhibiting the other, so the behavior of one neuron is trying to inhibit the behavior of the other. And if it's very strong magnitude, that's -10, it might give rise to chaos in both of them. So that's what we saw. But if it's excitatory and they're trying to synchronize with each other, they will give a very regular behavior. While it runs, let me see whether I have any more questions. Okay, I don't. Okay. Okay, it has completed computing K, and it has generated the time series, and computed the Hurst exponent and the sample entropy. And again, you can see here, wow, so P has become 0.9999. That means they are very synchronized with each other. And also the Hurst exponent has increased to 0 to 0.6, which is more than what we saw for the last simulation. And sample entropy is also low, 0.06, and K is in the same range of 0.1, which is still close to 0. So as expected. Now the two neurons are highly synchronized with each other. They're working in tandem, but bear in mind that, like, when we try to think of physical implications, like biological implications, what do this mean? So neurons synchronizing with each other might not be a good thing. So there are cases of epilepsy, and I personally work in this. Like my project is related to studying why epilepsy uh, occur through gap junction. Like when two neurons are highly synchronized with each other, why does it gives rise to epilepsy? So that epilepsy is not a good thing. And it this is like synchrony between highly synchronous behavior between two neurons is one of the factors. There are other factors as well that we need to think of, but that's one of the major factors, and that's what I study for my current research. So okay, we have looked into gap junction coupling. Now let's go into chemical coupling, which is a more complicated looking function to capture the chemical behavior between two neurons. Again, we run it is doing the same thing, except the fact that, like, it's a unidirectional coupling. So the coupling term is just in neuron X2, and this is capturing the chemical coupling between X. So the neurotransmitters are being released from X1 to X2. So that's why X1 is below and X1 is in the denominator and X2 is on the numerator here. Uh, for the second neuron. So we have just changed the system here, and the initial conditions are similar, and then you do similar sort of things. So you need to run this cell. Then this is the plotting function for running the simulations as well. Let's go with a weak negative coupling, so we can run this. Now, as the models become more and more complicated, the metrics might start acting funny, and they might not give you intuitive results. So you have to keep that. So watch out for those as well, just in case. So besides showing like how you can do all these things, it's important for me to also make you realize that not every analysis is also perfect. You need to know the limitations of different data analysis techniques, and especially in the age of AI, where you can just ask ChatGPT to do a lot of analysis or write codes for you to do a lot of analysis. You have to be very critical of any analytical techniques that you take into account. Yep. So just a PSA, I would say, and I try to remind myself that from time to time. So it has completed that. Okay, so keep in mind that neuron one is the signal is being propagated from neuron 1 to neuron 2, and as you can see here, the behavior between two neurons, the behavior uh, like across two neurons is quite different. So here the Hurst exponent is quite big. That means they are regular, and you can see from just an eye test that they are quite regular to this particular fixed point, I would say. And here they're bounded around the origin for the second neuron. So the behavior here is like the first neuron takes quite a lot of time to come to recovery before it starts firing again, and then there's a drastic recovery, and then it fires again. So but they are quite regular, so this will keep on repeating over time. So the k value here is close to zero. The sample entropy is also small. That means that it's capturing less complexity in a way. So there is not many chaotic behavior happening in both the neurons. But the two neurons are not synchronized. Even though they are regular, the two neurons are not synchronized, as you can see from just eye test from these two. So that's why gamma is very close to zero. And also B is 0. 0.9, in the range of 0.94. I have to do some more research on why the B value for two neurons. Maybe it's because two neurons, and like I need to increase the sample size. That's when B starts uh, behaving more correctly. But the qualitative values does act all right. So it's like 0.9486, which is low compared to when the two neurons are highly synchronized, when B is 0.99986 or something like that. Okay, that's for one. We can do like a bit more, a bit stronger excitatory chemical coupling. Let's see what happens then. Let's see whether there are any more questions. Can you use Kalman filters or just a dynamic linear model? Okay, been a question. Can you use Kalman filters or just a dynamic linear model to track the state? I don't quite know about Kalman filters, so I can't actually tell you uh, whether that will work. But I'm uh, open to discussions, and that's why I also want to learn from you. And Oren, if you are okay, we can chat after the session, if that's all right. Thank you, Oren. Yep. Yep, I have no idea what I know of Kalman filters, but I have never used it in my research. So it would be good to try some new scenarios. Yep. Thank you, Ade. Okay. Going back to okay. So you can see here. So the first neuron is acting in a regular fashion, but not quite regular, I would say, because there is firing and then it's settling down, but then it fires again, as neurons usually do. um, but there's a weird scenario coming up for the second neuron, so the neuron which is collecting the neurotransmitters from the first neuron. You can see here it's highly regular, so that means the second neuron is being pushed to a oh, what just happened? Why did it? Okay, sorry. Don't know why it magnified. But okay, the second neuron gets pushed towards an equilibrium point. So that means, so the neuron starts firing and then it just goes to a steady state. So it doesn't do anything at all. So it can't escape the 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 behavior after it has reached the particular behavior. So that's why it stays at that state, and it can mean a lot of different things. You can do you can come up with different physical interpretations out of this. So one of the physical interpretations that I would want to emphasize on is like it goes to a particular equilibrium behavior after it has fired, so it doesn't want to fire anymore, so it wants to stay at rest. So that's one of the things that I can think of, but depends on the complexity of the neuron models that you are considering. You see here the gamma value is highly asynchronous, so they are not synchronous at all. Again, however, there is no chaotic behavior between the two neurons, right? So that's why k is zero, close to zero, and sample entropy is also quite low. There is no high complexity because there is no chaos, and again the Hurst exponent is more than 0.5, as it indicates. Now we can keep on doing for Josephson junction coupling, more nonlinear coupling, and I think I don't have much time to go through all of them. But let me show you one example here, where this is another electromagnetic coupling. Oh, sorry, this is for the Josephson junction coupling. So that means we are including some periodicity in the current. So there's a periodic behavior that gets inculcated in the current that drives the neuron mechanism. And here, for this example, what did I okay, so for -1, when the two neurons are not, so the magnitude is not very high, but they are inhibitory to each other, they show quite a lot of chaotic behavior, both the neurons, and you see it's a proper Brownian motion, the behavior of the both the neurons. And k is close to 1, which is chaotic, and the gamma is highly asynchronous. That's why it's like in this range. The magnitude is 0.57. B is quite low, as you can see here, because they are not synchronous. And sample entropy is quite high, 0. 0.4, not in the order of 10 to the power minus 2 or 10 to the power minus 3. And Hurst exponent is again very low compared to 0.5. So it's like lower than 0.5. So that means the time series is highly anti-persistent. There's another one, another nonlinear coupling that you can look into, the memory strip coupling. And similarly the higher order coupling. So I'm gonna skip this, and in this case there are four. I don't know why is it vibrating. In this case there are four neurons that you can come up with, and then if you run this, keep in mind that the initial conditions are random. So even if you run minus 0.05 two times, the two results would be different. Yep. So you can run. I don't know why it is vibrating like that. That's very funky. I've never seen this before, but okay. Okay. So okay, I'll go to the slides to talk about a few more things before I wrap up. So these are the results that I showed to you from the gap junction coupling, the chemical coupling, and the chemical coupling. Okay, so now those are the, so you are varying the theta values every time, right? Now you can study how these quantities they change with changing the theta value. So the first one is for the gap junction coupling, the second one is for chemical coupling, and the third one is for more nonlinear coupling that I showed to you. Now you can see here that theta, when it's highly negative, then the Hurst exponent stays less than zero point 0.5. You see, until it reaches zero, when it starts going a bit up, that means the anti-persistence behavior is becoming persistent. And then as soon as it becomes positive, then it shoots up and it becomes highly persistent. The sample entropy stays low, 0.05. It keeps on, sorry, the sample entropy stays more here because it's complex here, and the complexity keeps on growing up until there's a plateau, and then as soon as it reaches zero, like the theta becomes zero, the sample entropy shoots down and it becomes very low, so the complexity decreases. And for the 0 1 test, the k value, it represents chaos, it stays very close to 1, and then as soon as theta becomes positive, it starts going down and then stays close to zero. That means there is no chaoticity, and like it's more regular. The gamma value, that means two neurons are whether synchronized with each other. When they're chaotic, they are asynchronous. That's why they're not close to one. So this stay very low until theta goes to zero, and then it shoots up and it stays close to one. And similarly for the other parameter, like the order parameter. So this is quite intuitive. Now, studying the chemical coupling with theta, it gives you some funky behavior because as I said, like the modeling might not be correct, and so the modeling might be correct, but like it might not be highly related to the data set, that like the parameter values that you are choosing from the empirical data. So you have to play along quite a lot to make sense of what these values actually mean, and whether this is the correct like quantifier to use. And similarly for the other nonlinear like coupling that I showed to you. Now there's a particular PSA that I want to share with you that I quite like. So an extra step for processing this running this simulation and like processing this data is you need to have an extra step before you visualize the data, and that's where pandas come handy. And i- it might seem that it's a bit of waste of time to start with, but it is not, because always try to separate the experiment and simulations from the visualization. Don't put it in just one code base, because who knows, like you might need to change your whole program to start with, or like the whole parameter values that you have chosen, and then you need to run it, and then you need to run it for like a week, and you don't want that. So it's better to have a step where you run the simulation and collect the data, and then you need to you need to have a separate code for running the visualization. So I learned it from this person, Tammy Calder, in one of the applied math conferences that I attended this year. And she talks about taming the chaos of computational experiments, and that's one of the steps that she emphasizes on, and I quite like that. I have used that since then, and it has changed my way of running programs. And so here is the code that creates the data file for the for these simulations, because these take quite a lot of time to run. And then you save them as I don't know whether you can see it, but you create a pandas data frame, and then you save it to CSV for the gap junction coupling. Now when you have saved the dataset, then you can just read the dataset using pandas as well, which is something like this. So this is from the gap junction dataset that you generated. It can come from like uh, from real world data as well, which will have the coupling strength and accordingly what the values of age, like the Hurst exponent, the sample entropy, the cross correlation coefficient, the 0 1 test value, and the Kuramoto order parameter look like. And then you can just write another code for running the simulations, and that's it. The Shiny app that I was talking about can be accessed from this link. I'm not going to click on this link because I don't want everyone to go at the same time. But this is something, it's a very uh, low key app, I would say. And I used ChatGPT for the front end because I don't have much experience on the front end aspect of building things. So the back end is written in RStudio. And the front end, I have used ChatGPT to like come up with a very low key app, but it still needs a lot of work to make it aesthetically better. But it gives you a minimal, so it works minimally and it gives you the results that you want to see. Okay, a bonus slide in the sense, like we were just talking about two neurons, right? So, and you saw how complex the behavior becomes and how much time it takes from time to time. So there's network X that can help you uh, like distribute the dynamical behaviors of different neurons spatially, right? But the time complexity still is not solved. It's still hard. So because the neuron, like our brain and our nervous system has neurons all over connected like this, right? So that's how complex our nervous system is. And you can use network X to run simulations for hundreds and thousands of neurons. um, so I have done it for 50 here, and you can see I have placed the so I have the topology of the network that I've considered is a random Ardos Renyi graph, which has a certain probability that you can choose, and that's the function that runs the uh, simulation for the dynamical system of the neurons all over like 50, all across 50 neurons. And then it collects the data set, and it collects the results. But as I said, because of the high complexity, high coupling strength between two neurons, uh, using parallel computing is not an option until and unless the data is very sparse. But even though it's sparse, uh, it's not going to be easy using parallel computing. So what's the alternative? I don't know. It's a big question, and like if someone in the audience has some insights on like how to make them better, I would be very grateful. So yeah, as a as I wanted to mention the fact that it's not only me giving the tutorial but also me learning from the audience as well. So if anyone has any ideas, please share with me. I would be very interested to know. A bit of summary, and again, excuse my use of cartoons. We used coupling and saw different coupling strategies, and we saw that coupling induces chaos in the inhibitory regime. Now, excitatory coupling, when the coupling strength is positive, and its more positive values drive the coupled system into exhibiting bursting, which is a normal neuron behavior, and also both neurons synchronize. In electromagnetic coupling, however, excitatory coupling drives the system to decay oscillation. So something like a straight like a the as I showed you in one of the simulations, that it goes to a steady state, falling into like a symmetric equilibrium point. And now the future work that I was talking about, can we move to a GPU accelerated framework using the package Q, QPy after QDAPy? I don't know. I haven't tried it yet, but that's one of the things that I want to try. And as I showed the network X simulation, I want to run the network X simulations and like collect the data, and then try to see whether we can apply our different metrics on the big data set. I'm just gonna stop here. Yeah, big data set. Now I'm also writing a blog on it, and it will come soon. So keep an eye out for that. And acknowledgements. So this work has been spread across New Zealand, Auckland University of Technology, where my one of my colleagues is based in. Massey University in New Zealand, where I was based in previously, and now I'm based in Dublin, and my other colleague from India. So this is the time series, like the tutorial on time series analysis of couple neurons, and you can find it in this openly available paper. There is a repository along with the paper, but you can also like refer to the repository that I shared today. So it's the same thing, but the shared repository for today is more cleaned and like the cleaner version, I would say. So any that's it from me. Any questions, comments, suggestions? And okay, I want to tell you that like I used ChatGPT for creating this cute cartoon. I simulate a simple neuron, and when I'm happy, but when the couple neurons come in, there is chaos and a lot of like raggedy jaggedy data set, and like different complicated values that I need to deal with. And that's what I look like when I deal with these kind of systems. Okay, that's it. Any questions, comments, or suggestions from the crowd?
Hi, Indra. I'm helping co-hosting this, and we
Oh,
do have
okay,
a couple questions left in the chat.
okay,
Um, so we have one from Orange. They ask, so for a large network, there likely would be emergent behaviors so long as the units aren't in some critical domain. I'll let you look at that. I think that is just maybe a response. And
yeah.
then there's a question about your slides too.
So for large number, there likely would be emergent behaviors so long as the units are in some. Okay, okay, that's a very good point. Hmm. Uh, so yeah, I need to see whether I can quantify those behaviors using proper metric. The emergent behaviors, there has been a lot of studies on emergent behavior, because when there's so that's the whole is more than the sum of parts kind of emergence behavior, right? So that's what you're referring to. And that gets very complicated as well when we try to quantify those behavior. And yeah, okay, like magnetism or earthquakes. Okay, that's very interesting.
And it looks like Ada is asking if we will be getting a copy of the slides.
Yes, yes. What I will do is like I will um, on the repository itself, I'll upload a PDF, because I'm using Keynote currently, so that's why I'm not sharing it in the, because not like I shouldn't assume that everyone uses Keynote, so that's why I'm. But can I share a PDF now, because I can just convert it into a PDF right away and share it in
Yeah,
the text.
you should be also able to share it in the resource tab in this
Okay,
session.
I'll just oh, I think I already do have a PDF if I'm not wrong.
No
Okay.
worries. While you're uploading that, I just want to make a comment since we are at time. I just saw like there's
Yep.
another question in there.
Yep.
But we can continue this discussion in the Discord. That link is available in the reception area. And a recording of this session will be available shortly for rewatching. And for those who are interested in just more casual conversations, the lounge will also be open in the reception for small group discussions.
Okay, how do I go to that?
Um,
So
I okay, let me see. You would have to click the back button and
the
let
back
me
button, but
yeah,
if I
like
click the
but after we're done with this session, because then you'll
okay,
just
yes, okay. Okay,
it
that makes sense. Yeah,
it should take you to
yep,
the main global site. I wish I had it in front of me to show you.
that's all right.
If Patricia is listening, she knows it a little bit better. So
Okay,
yeah, she's hopping on.
Yeah, you're right, Claudia. So as soon as we'll end the session. Thank you so much. Oh well, I don't know if you wanted to answer that question, but yeah, when we end the session, you'll just go back, press the back arrow, and then you'll be at the main lobby to either go to the next session, which I believe
okay,
all the sessions are done for today, and then or you can go to the Discord and you'll see um the different talks or different
okay,
channels.
cool. There's one question from the chat. Should I answer it here or
Yeah.
like? Okay, let me. Is it possible to use? I'll just repeat the question. Is it possible to use a computational graph architecture framework like Python? Yes. So that's my next one of the next goals. But again, I have to learn a bit on PyTorch and TensorFlow because I haven't used that quite often. So I didn't put that on my slides in the future slides. Uh, this may help you leverage CUDA capabilities to scale your solution. Okay, yes, that's definitely. I want to try that out as well. Thanks for like sharing that. Yeah.
All right.
Okay.
Well, thank you guys so much for staying on and asking your questions. I'm going to go ahead
Thank
and
you.
end the session. And thank you, Indra, for leading this.
Thank you, Claude. Claudia. Okay.
Yeah,
Okay.
yes. I know I
Okay.
jumped in late. But yes, if you guys want to continue this, there is that reception area that you can join. And y'all have a great day. Thank you.
Thank you. Thanks for joining. Bye bye.